All right, well, we're going to be moving away from nomenclature now, and we're going to be spending a lot of time looking at the stability of organic compounds. And we're focusing mainly on alkanes and cycloalkanes in this chapter. But a lot of the things that I highlight in this part are going to be applicable kind of across the board for all functional groups. And so that's going to be forming the basis of our discussion for mo pretty much the rest of this chapter. Um, but before I move on, I want to address one thing, and that's kind of the relationship between this chapter and our first unit. In the very first unit, we looked at drawing constitutional isomers. Um, because alkanes can have a variety of different chain lengths, or it's very sometimes somewhat difficult to see if you can recognize a couple of alkanes or the structures of alkanes as isomers or as different compounds. Or if they're even identical, because one compound can be drawn a whole bunch of different directions and yet still be the same compound. So the trick for recognizing constitutional isomerism in alkanes is name the structures. And if the names are the same, as long as you did both of them correctly, if the names are the same, then they're identical compounds. But if they're not the same, like maybe the numbers are different, maybe all the substituents are the same, but the numbers where they're located are different, then those would count as constitutional isomers. So if we look at these pairs of compounds, let's just start with the one on the left here. What I'm going to do is just name them and see if the names are the same. So our parent chain for this one here, I'm going to number it like this. Okay. And I've numbered it kind of like skip through a few of our steps, but I found the longest parent chain and then I numbered it so the substituent encountered first gets the lowest possible number. So if I were to name this one on the left, it would be 2,3-dimethyl pentane. Now let's do that with the one on the right here. And again, I'm kind of skipping through a few things. Assuming you've worked on nomenclature and that you're getting pretty good at it. But the longest parent chain here is this, and I'm numbering it so that the substituent encountered first gets the lowest number. So we note with this is that it has the same name, 2,3-dimethylpentane. Same name means they are identical compounds. They are not isomers. They are identical. Now, with the pair on the right, I'm going to approach this in the same way. Going to find my parent chain. And again, like I said, I'm kind of skipping through some of the steps, step-by-step process. But note that when we name this, so there's a methyl here and a propyl here, we got 3-methyl, 4-propyl heptane. Now on the one on the right, this is going to be our parent chain, and it's numbered so that the substituent encountered first gets the lowest possible value. Notice what happens though with where this methyl group is located. That methyl group is now on 2. The propyl is still on 4, but because the methyl is now on 2 instead of 3, that's a different location. It's like we physically took the methyl off of 3 and put it on 2. And so we would call these constitutional isomers. So that's kind of the trick when it comes to identifying constitutional isomers in alkanes. So let's get to the bulk of what we're going to focus on for the remainder of the chapter, and that's stability. So I'm going to spend a very brief time looking at stability between compounds, and then I'm going to spend a lot of time looking at stability within one compound. And so when it comes to looking at the relative stability of alkanes, I'm going to look at comparing constitutional isomers. So I want you to look at the three structures of these compounds. They're all the same. They're the same molecular formula, but they're constitutional isomers. They have different connectivity. Now, even though they have the same molecular formula, they are not equal in stability. Essentially, the way that we test this is we take the compound and we ignite it. Okay. We basically calculate the heat of enthalpy, which we obtain by combusting it. So each of these is reacted with the same amount of oxygen to get the same products, same ratio of products, but they each release a different amount of energy. The rule of thumb is the least amount of energy released, or the smaller that value, the more stable the compound it came from. Because you kind of think of it like the larger the value, the more pent up energy there is, potential energy in that compound. And more energy, just to review, more energy means less stability. Less energy means more stability. So with the this highly branched alkane here at the bottom, notice that its heat of enthalpy is negative 5,452 kilojoules per mole. Now the number's not important. I'm not going to ask you for that number on an exam, but the trend is important. We get a little less branched, the amount of energy goes up a little bit. And then a completely straight chained alkane has the highest amount of energy. And the simple takeaway from this is that branched, and I want to highlight constitutional isomers, are more stable than just straight chain constitutional isomers. And that's pretty simple, straightforward, just discussion of stability between compounds. And what I'm going to look at for most of the rest of the chapter is what if we're looking at just one compound internally? And here's where this arises. I'm going to turn my camera on for a little bit because I want to look at a simple compound ethane. Now, I highly recommend if you have a model kit, pause the video, get your model kit, and kind of build along the compounds with me. But I'm going to look at ethane here. So I'll draw the structure here. Okay. Now, one of the things to note about single bonds is that they are free to rotate around. You can do this on a model kit, and this is what happens in real life. So these carbons are constantly rotating around like this. And then that's true for these single bonds and these straight alkanes. Um, what I also encourage you to do is make a pi bond, make a double bond. And what you'll see is you can't rotate around a double bond. So these single bonds, are kind of special in that regard, in that we're free to rotate around the single bond. Now, this rotation causes different amounts of stability within this molecule. Not, and if I were to kind of spin this around, I'll just spin this around the front, and I were to take a picture of it and freeze it in time and get a snapshot, that snapshot is what we call a conformation. It's the three-dimensional arrangements of these atoms. And in reality, because numbers are infinite, I could get an infinite number of conformations because I can go zero point 0.1 degrees and then 0.11 and 0.111 and so on. I could go crazy with all of that, but I'm not going to highlight every single infinite possibility. But the key thing to remember is that these conformations result in a different stability as I rotate around the carbon. The molecule might not be as stable in one conformation as it is in the next. Some of the conformations might be equal in energy. So one of the ways that we help us describe this without a model kit, but be able to describe this in two dimensions, like on a piece of paper, is to draw what is called a Newman projection. So I'll just shut this down for right now. And a Newman projection allows us to go from looking at a compound on the from the side. So if we draw the kind of structure of ethane, like a skeleton formula like we see here. A Newman projection allows us to look at it from the front, like you're looking at this carbon right here. And this becomes a lot easier to kind of see how these groups are rotating around that carbon by looking at it from the front. It's kind of hard to see if you're looking at the back, or from the side, I should say, what that looks like. It's much easier to look at it like this. Now, that's easy to show in 3 dimensions. How can we do that in 2 dimensions on a piece of paper? Okay, so that's where Newman projections come in. Now, the first thing I want to do is highlight some new type of bond notation. And we're going to dive deeper into this later on down the road. But if we want to represent a group going in a particular direction in 3 dimensional space, we use these wedges and these dashes to show directionality. If you have a solid wedge, that means that that group is coming out at you. And a dashed wedge means that that group is going away from you. Now, in order to go from this kind of side on view, like it's that's how we normally view things on paper, to a head-on view, we rotate the molecule around a little bit. So we rotate it a little bit, we get this sawhorse conformation. I'm probably not going to say another thing about a sawhorse, because if we rotate it 90 degrees, we look at it head on. So this is essentially what we're doing. We're starting here, and I rotate a little bit, that's like our sawhorse, and then I rotate it completely, and now you're looking at the compound head on from this direction. And that's what gets us to a Newman projection, is we're imagining rotating it from a side-on look to a head-on look. Okay, so let's look at how we draw Newman projections. Okay, so this is the compound that you see on the page. And the red spheres here are the bromine atoms. And then the white spheres are the hydrogens. Notice how the bromines are coming out at you. That's what those solid wedges mean. Okay, so the bromines are coming out at you. The hydrogens are going away from you. Okay, now what we're going to do is observe this compound as if we were over here on the left and we're looking at it head on. So I'm literally taking this and rotating it around like this. Okay. So if you are looking from the left, that bromine that's with that solid wedge would be going upwards and to the right. Now you say, what about the hydrogen? I'm going to draw the hydrogen in here. So there's the hydrogen, and I'll draw the hydrogen here. So that bromine would be up and to the right, and that hydrogen would be up and to the left. Now, what about this methyl group here? We would just say it's going straight down. Now, I'm just going to focus on that one carbon right now, the one with the red dot on there. So the carbon that we're observing directly, in a Newman projection, we would draw it like this. That group going up and to the right goes here. The group going up and to the left goes here. And then the group going downward goes here. I'll just draw a CH3 specifically. Now, how do we draw the next carbon over, that carbon in the back? Well, in order to draw it properly, we need to know what direction the 3 other groups are going on it. So in this case, that bromine over here would be going down and to the right, and this hydrogen over here would be going down and to the left. And then this methyl group, we would say, would be going straight up. So here's how we draw the rear carbon of a Newman projection. This is the front carbon. This is the rear carbon. We use a circle, and then the group going up is here. So that's our CH3. The group going down to the right is here. That's our Br. And the group going left is here. That's the hydrogen. Now, those are our two pieces. We're going to put them together, one on top of the other. So it's going to look like this. Add them together. And actually, I'll use the same colors I did before. Oops. So there's my rear carbon. Here's the front carbon. On the front is a CH3 going down, Br going up and to the right, and hydrogen going up and to the left. And then on the back carbon, I'm going to draw that CH3 going up like this. The bromine going down and to the right is here. And the hydrogen going down and to the left is there. And so that's kind of it in a nutshell when it comes to drawing Newman projections. Where things get a little tricky is what if we're observing it from the other direction? So I'm going to get to that. I'm going to do a few problems, and then I highly recommend that you practice these Newman projections, because in our next lecture, we're going to look at the implications of how the energy implications of what happens when we rotate around that carbon, and how we're going to use these Newman projections to show all the various conformations as we rotate around a carbon-carbon single bond. Okay, so let's start here with letter A. So now, as this implies, we're going to be directly observing this carbon. That's going to be our front carbon. Now you notice like, well, where's the dashes and wedges? I'm going to give one of these, I'm just going to make it a solid wedge. So there's a methyl there with a solid, and I'm going to make this one a dashed. Now what I want you to do, and actually, sorry, first, and I'm going to do that with the hydrogens over here. I'm going to make one a solid hydrogen and one a dashed. What I want you to imagine is that you are over here looking at this molecule from the side. If you were looking at it from the side, that CH3 with the solid wedge would be sticking out right at you, and it would be going upwards. And then the hydrogen on the next carbon with the solid wedge would be sticking out at you, but it'd be going kind of downwards. And then you'd say the opposite for the other CH3 and the hydrogen. Now what you're going to do is walk around and now look at the compound from head on. That CH3 that had the solid wedge will now be up and to the right, and the CH3 with the dashed wedge would be up and to the left. And this guy right here would be sticking straight down. So if I draw the front carbon for that, this is what I would be observing. I have that CH3 down there. There's that CH3 that's up and to the right. And there's the CH3 that's up and to the left. Now I'm going to do that same exercise for the rear carbon. I'll mark it in blue. So for the rear carbon, start with a circle. That's the carbon. That's our symbol that represents that carbon. And I have a CH3. This guy is going up. This hydrogen is going to be down and to the right. That's this one here. And this hydrogen will be down and to the left. Again, assuming you're looking from this direction here. So now I'm going to put these two things together. I'm going to take that front carbon and move it right in front of the rear carbon. So here's the rear carbon, CH3, H, H. Here's the front carbon with CH3, and then CH3, and CH3. Now let's take a look at B. Again, what I want you to do is start off by imagining you are right here and you're looking at the compound from the side. When you do that, this chlorine is coming out at you. And then let's draw the hydrogen in. That hydrogen's going away. And then this chlorine over here is going away from you. And this hydrogen would be sticking out at you. So then you take a little walk, and now you're going to observe it head on. So when you do that, then this group right here, whatever that is going straight down. This chlorine is going up and to the right, and this hydrogen is going down. I'm sorry, not down. Up and to the left. So my front carbon will look like this. All that CH3 down. This chlorine will be up and to the right. This hydrogen will be up and to the left. Now, when I go to the rear carbon, again, I'm still observing the compound from this direction. This group, whatever that is, will be going up. This group here will be down and to the left. And the hydrogen will be down and to the right. So my rear carbon looks like this. Use a circle, that's the symbol for it. This group's going up, it's a CH3. The group down and to the right is a hydrogen, and down and left is to the chlorine. Now I'm going to put the two together. I'm going to take the front carbon, move it right on top of the rear carbon. So there's the rear. Here's the front. And this should be the chlorine. And there's our Newman projection for that compound. Now, where this gets a little tricky is what if you observe from the other direction? So we're observing this carbon right here. And then I'm going to draw in, so if that this CH3 right here has a dashed wedge, I'm going to draw the hydrogen here with a solid. I'm going to do that over here with this one. Hydrogen and hydrogen. Now it changes the game a little bit because again, if you were observing this compound from this direction, that hydrogen right here would be coming out at you, and this CH3 would be going away from you. So if you walk around, now you're still going to see that front carbon with those two groups going up, but this dashed one would be up and to the left, I'm sorry, to your right. And this hydrogen would be up and to the left. So really the same direction, but the right hand and left hand flip. That's all that is different if you're observing from the other direction. And so with these, that hydrogen would be up, not up, down and to the right. And that one would be down and to the left. Okay, so let's draw what our front carbon look like. Again, we're looking at this carbon for our front carbon. So this group right here is straight down. And so that's a CH2, that's an ethyl group, so we can put that there. Alternatively, you could do this. I will say either one of these is equally valid. That's your ethyl group. So you could do one or the other, just so that everybody knows where all the atoms are at. I'll just write in that. And then this hydrogen would be up and to the left, and this methyl group would be up and to the right. Now the rear carbon in the back, this group would be straight up. So we use a circle, and the up group is the ethyl, CH2, CH3. The down and right would be the hydrogen, and the down and left would be the hydrogen there. And like before, I'm going to merge these two together to make the Newman projection. And then my front carbon looks like this. All right, so the only thing that changes if you're observing from the opposite direction, only thing that changes is what is left and what is right. All right, so I highly encourage you to work on some problems on this. Okay, look in your textbook for some problems, and because what we're going to do is we're going to take these Newman projections and use them to visualize the relative stability. What happens when I start to take one of these carbons and spin it around? What happens to the internal energy and to the internal stability of the compound as I rotate it 360 degrees around that single bond?